All right, so test on Monday, and we're going to do a little bit of review work here. The first thing that we're going to take a look at is going to be comparing geometric and arithmetic. All right, so we're going to take a look at something here. Let's say that I'm giving you these 2 points of data. Is that arithmetic or is that geometric? It could be both, exactly. And what would it need to be arithmetic? It would need a 12, yep, exactly. What would it need to be geometric? 16, awesome. And then since it's arithmetic, is that a common ratio or common difference? Common difference. So arithmetic, we're always doing our adding and subtracting, talking about the common difference. If it's geometric, we are talking about our common ratio. Perfect. And this is a good example here too, because you won't always be given 3 points so that you can tell, but there might be other clues that give you a hint as to why, as to what form it is. So like if I said something like, awesome. So the same example, I said 4 and then I said 8, and I said find the percent change. What does that tell you about the third term in this sequence and the sequence in general? 16, and we call it what? Geometric, exactly. So just a good thing to know that you won't always be given all of the information in the sequence to make it real obvious, but there'll be clues in the question there to be able to get there. So this percent change here. So for doing our common ratio, what do we do to find our common ratio? Correct. So we'll just do the one, 8 divided by 4. So we know that our common ratio is 2. So then what would our percent change be if our common ratio is 2? Would it be 200? Who thinks it would be 200%? Raise their hand. Who thinks it would be something else? And what else? Yeah, 100%. Why is that? So you do 1 and then what? 1 plus 1. Yep. It has to equal the parentheses. Yep. So just a real quick, cleaner explanation of that. Our common ratio, that's always going to be the full thing inside of the parentheses. It's going to be everything inside of there. So if this is 1 plus 1, it's the same thing as 2. So it's going to be the whole thing inside there. Our growth / decay rate, in this case it's growth, is going to be just one piece that's inside of that parentheses, and it's going to be that piece right there, and that's it. So that's the only thing that we need for the growth / decay rate or percent change. Growth / decay rate would be the same thing as percent change. They're kind of used both ways. So yes. You know, whichever way works best for you. I mean, I'm going to understand that if you say, hey, this is growing at that, I'm going to understand that that's 3%. If you said that it's growing at that, I would also get that. So I'm not going to be super picky on that. I would keep it consistent for you so that every time you do it the same way, so that there's kind of a methodology there. So that I'm not jumping back and forth and maybe throwing myself off when I don't need to be. But yeah, so either way works. Whichever way you would prefer to do it is perfectly fine with me, just so long as it's obvious whether this is a growth or a decay, because that could be a 3% decay or that could be a 3% growth. In this case, well, if this was in here, it would be a growth because we have the plus sign there. All right. So I think that makes sense. So let's just do one more of these because it seems like we just want to make sure that we're really solid on this. So u of 1 is equal to 1,000, and u of n is equal to u of n minus 1. We'll say 1 minus 3 where n is greater than or equal to 2. Why don't you do this and tell me what my common ratio is and tell me what my growth/decay rate is. Give you a minute to do that while I pause the video. So the common ratio is this whole piece inside of here, so that'd be 0.75, and then our growth/decay rate is just this piece here. We know that it's decay because of this, so decay, and it's just that piece there, 0.25 or 25%. It looks like basically everybody had that, so I'm really happy about that. Yes?
How would you show if it's increasing by 75%? Because would you keep the, I don't understand how that works.
So how would you show if it's increasing by 75%? Do you mean increasing as in the common ratio? Well, yeah, do you mean increasing?
Yeah, that's what I mean.
Okay. So that'd be something like this. Whoops. N minus 1 multiplied by, and it's increasing by 75%, so you're calling that the common ratio.
Yeah.
In theory, if the common ratio is 0.75, that's going to make it decrease. But if you're trying to say that it should be 1.75, because if I take 10 and I multiply it by 1.75, this is going to grow. This will go up. But if I take 10 and I multiply it by 0.75, that'll go down. So it's not possible to have it grow at 0.75 unless you're saying 1.75, and then you're saying your percent change is 0.75 or 75%.
Okay, that makes a lot of sense.
If it's for this one, would you put okay, so this one here would be a decay. So our first step is of course we put the negative in, and this is my common ratio because this would be the whole thing inside there. So I'd actually put 0.25 because I want 1 minus that number to equal 0.75. All right? Cool. Okay, I think that we've hammered that thing into the ground. Let's go on to something else. Why don't you do this? Use recursion to write a sequence. Oh my gosh, that was terrible. Sequence. Everybody work. That's not it. Use recursion to write a sequence. Everybody spend a second and use recursion to write a sequence. Back in here. So bring this back in here. Yes. Yep. So recursion. Use recursion. So everything that we've been doing in this is writing recursive sequences. And what does this word mean? By definition, what does this word mean? Who wants to try to define this? Who wants to define the word recursive or recursion for us? Reoccurring. Keep going. It's a continuous pattern, but there's a key piece to this pattern. A continuous pattern of numbers. Infinite. These are all ideas. The key thing about this is that all those things that you just said is more about a sequence. Recursive means it's dependent upon the term before it. So everything we've been doing with this u of n is equal to u of n sub 1. This part of it is the piece of it that makes it recursion or recursive, because it's saying my term that I'm looking for is dependent upon the term in front of it. So that's the only thing that word recursive means, is just that I cannot find the term I'm looking for unless I know the term before it. That's what the word recursive or recursion means. So going back up to the question here, use recursion to write a sequence. I would be writing a sequence that would be dependent upon the number before it. So there are literally infinite answers here. 1, 2, 3, 4. Would that be an arithmetic or a geometric? Arithmetic, because I'm just adding 1, because there's a common difference. 2, 4, 8. Be a geometric, because I'm multiplying by 2. So all that recursion is just saying, to find this term, I need the term before it. To find this term, I need the term before it. Find this term, I need this term. And that is what we've been saying in all of our sequences the whole time. That this piece here is what defines it as a recursive function, or sequence, I should say. So I just wanted to throw you a variation on this word here too. Make sure that we're understanding what the word recursion means. But sequence is just most of what you guys were giving me for answers was just like, it's just a series of numbers. It's just an orderly system of numbers. So, all right, let's see here. What was the other thing I was going to do? Yes, so let's take a look at some graphing ones here. So, toss some graph paper in here, but you can always just draw it. If I'm, let's call that 10, 5, call that 20. So I'm going by 2s here. 1, 2, 3, 4, 5. Going by 30. 1, 2, 3, 4, 5. Going to 40. So if you're given this, write the sequence for this given graph. Write the sequence for this given graph. I'll give you guys a minute to work on that. So let's go ahead and write this sequence here. Who can help me out with writing this sequence? Mr. T. Mr. T. Can I have you help me out and write this sequence, please? Awesome. U of n.
Yes.
Mm-hmm.
U of n minus 1.
Mm-hmm.
Parentheses 1 plus 1. Or times
1 plus 1. And then is that it? All right. So on this one here, I would probably mark this wrong. Why do you think I would mark this wrong? What? Hey guys, we don't all need to comment. Okay. Why? Who can help him out? Who can help him out with the pieces that he's missing with this? Let's go right over there.
U of 1 equals 2.
Okay.
And
Greater than or equal to 2. So every time that you're writing a formula or rule, be sure you have all 3 pieces. It'll happen this year. It will happen every single year. Somebody will forget to write n is greater than or equal to 2 on all their problems, and there will be points that they will be losing on those. And sometimes they're nice, and sometimes they're not. So just be sure and just think, okay, if it's a rule, I need 3 pieces. I need 3 pieces. I need 3 pieces. So you will see something like this. You will see pieces where they're giving it to you graphically, and then you have to interpret the common ratio or the growth or decay rate, or write the rule, or basically any of those pieces. So be familiar with what it looks like to graph that. Let's do this. Let's graph one now. So I'm going to give you a rule, and I want you to graph this one. So equal to 10. We're going to use our same scale. 10. Hopefully I counted that right. Okay. So u of 1 is equal to 10. Then I'm going to go u of n is is equal to u of n minus 1 multiplied by 1 minus 0.2 n greater than or equal to 2. So if you can't read this, I'll write this again here. This is u of n is equal to u of n minus 1 multiplied by 1 minus 0.2. Why don't you go ahead and take a second and write that? If I write that, I mean graph that. So we're going to take a look at graphing this here. So our first term, we'll call this one here. Let's go by 1/2 on this scale. So we'll call this 1, call this 2, call this 3, 4. So our first one should be really easy. That should be a gimme. 2, 4, 6, 8, 10. All right, so our first one should be really easy because they're giving this point to us in the problem. U of 1 is equal to 10. Go over 1 up 10. Now what's our second number here? 2, 8 would be correct. So far we've got 10, and then we've got 8 because we're just taking 10 and we're plugging that in here, saying times by 0.8, which is what's bringing it down to 8. So let's go to 2 here, go to 8, and then after that, what's our next point? So now taking 8 times by 0.8, 6.4, something like that, and so on and so forth. It'll probably be. Mm-hmm. Say that again. Yep, because that's the definition of a recursive thing, is that to find the term that you're looking for, you need the term in front of it. So if I'm looking for my second point, I need the first point, and they've given that to us. If I'm looking for my third point, then I take what I found from the second point, and I can plug that in. Does that make sense? Yeah. Okay, sounds good. So yeah, and notice that this doesn't do a great job, but let's say that this wasn't 1. Let's say that this was, I don't know, negative 20 for some reason. Do you guys kind of see how this is making a little bit of almost like an exponential curve there? That's something to notice with these. So when it's growing, it's doing something like that. And when it's decaying, it's doing something like that. It's getting closer and closer to 0 or closer and closer to infinity. So sometimes in our next units and whatnot, there'll be some different wording where it'll be like exponential growth. And that's just what it's referring to, is basically this graph that is shooting up. So let's do our last one here, then we're going to take a look at the homework. So let's do our last one, which is going to be right here. Let's grab this guy. So this is from the notes from yesterday. So why doesn't everybody pull out the notes from yesterday, and let's do number 3. This will be our last thing before we take a look at the homework. All right, so why don't you guys do this one, and you'll need your calculator out to be able to do this. So as somebody pull their calculator out and start doing this, and I'll give you a second to do that. Let's go ahead and look at this one here. So Gloria deposits $2,000 into a bank account that pays 7% annual, and this is a key word for us here, annual, interest compounded annually. This is also a key phrase here, compounded annually. This means that the bank pays her 7% of her account balance as interest at the end of the year, and she leaves the original amount and interest in the account. When will the original deposit double in value? So, first piece here is we know. Why doesn't somebody walk me through this? What did you guys get for this one here? Let's go right back there. Yep. U of 1 is equal to $2,000. Is that really hard to read? Yes. All right. So U of 1 is equal to $2,000. Okay.
And then I said,
n is greater than or equal to 2. Yep. Mm-hmm. U of n minus 1. Mm-hmm. Plus 0.07. Perfect. This looks great. Is it? Yes. Ah, that. Why would you want to change this to a 0? Right. So a little trick. Your equation was not wrong. You would totally get it, and it would totally work. But you just have to remember that basically you started with 1, and that doesn't count as a year. So in this case, starting with 0 would probably help you avoid being off by 1 at the end. So if you change that to n is greater than or equal to 1. So just remember that this number right here, we're setting this number. So set this number to make your life easy. So in this case, we would like to set this to 0, because then when we get to year 1, then it'll be n is equal to 1, and we'll know what that is. So let's plug this into our calculator here. We'll pull that up here. Make sure I'm still in sequence mode. Looks like I need to get over there. What? All right. So jumping up here, so we're going to set our n minimum is equal to 0, because you know that's going to be a little bit easier. We go u of n minus 1 multiplied by 1 plus 0.0, what's my number? 0.07, thank you. 0.07. And then our u of 0 is equal to, Gloria starting with $2,000. So did you check? So the first thing is, if your calculator freaked out, I usually like to try to jump straight into my table set to make sure that I'm not starting at like 2006 or something like that, and then the calculator would freak out at me because it'd be huge numbers. So my table start looks like I'm going to start at 0, and I'm going up by 1. So that's a good start there. So I'm going to go to my table now, so second table. And then I'm just looking for when does this cross $4,000? And it looks like it does it right there, year 11, because I'm looking for it to double. 2,000 times 2, 4,000. Looks like it crosses at year 11. So this. Did you set your u of 1? Did you set your this equal to 1 or equal to 0? Then that's why you got it year 12, because you're saying that your first initial year is n is equal to 1, right? Because then you're saying my first year I have $2,000, and that's why by the time you get down to your 12th year, you're there. Whereas here we're saying our starting value before we even hit a year. Yep. You don't have to, but just so long as you know that you're off a year. Yep. You can do that. It's just a really good way to get a wrong answer. So just watch out for that type of stuff. Just use this number to your advantage, because you can set that to whatever you want to. So set it to the thing that's going to make your life the easiest. Math people are all about, they will do all the work all the way to the end every time, but they are very lazy. So they want to do the least amount of that work, but they'll do all of it if it's needed. Yep. All right, so let's take a look at the homework. Homework is going to be growth and decay. This guy here. So looking at our homework here, this is our review worksheet. So be reviewing for the test. So let's do number 1. So we'll do this one. It's got multiple parts to it. They're all pretty fast. Once it gets down to the end here, it gets a little bit annoying. But ultimately, if you can do number one, you'll be able to do probably 85% of what you need to do on the test. So, so if you can do number one and know what each of these pieces are, you're looking at a middling B. So number one, then let's jump down. Let's do problem 3, but let's do B and B, incorrectly labeled there. So problem 3, so we'll just do B, and it should be D, but it's actually B. So we're doing 1 all of it, 3 B and B, and then let's do number 7. I don't like number 5 and 6. I think they're kind of dumb. So kind of some really odd numbers here for you. You're doing number 1 all. You're doing number 3 B and B, and you're doing number 7. And if you need more help, take a look at those other problems. That's good. These application ones are not so good, so you can take a look at the notes from the application day if you want another problem to do one of those. That's it.